Okay. Okay, so we now have basically everything on the table in front of us, the basic ideas of how an interferometer works. We haven't gone through the detailed analysis of it, but we have all the numbers in front of us, and all these numbers that I've given to you are good to within about a factor of 2, just derived by these simple considerations. But in the end, we need to understand more quantitatively. We need to be able to figure out the spectral density of the gravity wave noise. We need to understand how that spectral density is used to determine the accuracy of measurements of gravity waves, how we get a signal-to-noise ratio out. So there's a lot of detail, elegant detail yet to be gotten, but the key ideas are just as simple as that and presentable in about a half an hour of time. So what I'm going to do now to spend the remainder of today and all of tomorrow talking about fundamental physics that underlies these gravitational wave detectors. We'll do fundamental physics on these idealized interferometers, but then we will begin to consider some more sophisticated issues that make up a real interferometer. And next week on Monday, Alan Weinstein will give a lecture of an overview of real interferometers and what are the issues, new issues that you have to face with real interferometers. But I want to get the fundamental physics that we need for this subject and now out in front of us in the remaining half of this lecture and all of tomorrow. And there's a fair amount of fundamental physics. Let me just give you a sort of a list of things that I want to do. I'm going to do them fairly quickly. I will give you reading on them. Most of the reading is small sections of the textbook for Physics 136 that Roger Blanford and I are writing, but it's just little pieces here and there in the textbook of the fundamental underlying physics. Pardon? It's all on the web, and so I'll give you particular sections, and you can just go on the web and pull it down. Okay. Okay, so let me just tell you what issues in fundamental physics I'm going to be dealing with. Let me find the... So, I keep talking about a beam of light. So we need to make that precise. What is a beam of light? And so we will talk about Gaussian beams of light. And at one point in the course, we will explore the possibility that in LIGO 2 we may not want to use Gaussian beams. Everybody uses Gaussian beams, but there are reasons why Gaussian beams might not be what we want. And so we will explore other shapes of beams later on in the course. But everybody, almost everybody in all applications in optics uses Gaussian beams. And so that's what I want to lay on the table in front of us. We'll talk about manipulation, just in qualitative terms, manipulation of Gaussian beams with mirrors and lenses. We've got a Gaussian beam coming out of here. It's going to go and interact with all these mirrors in here, and it's going to have to be given just the right transverse shape in order to match properly into these cavities. We've got an optical cavity here, we've got an optical cavity there, we have a subcavity here. And so it's a little bit complicated. You have all these various cavities, but the beams have got to be manipulated in order to fit into those. And I'll give you the foundations for that, but later on in the course, somebody else will lecture on details. In order to be able to analyze an interferometer like this, and I will give you the task of analyzing it on the homework, you need to understand issues of reciprocity relations for the reflectivity and transmissivity of mirrors and beam splitters. And these reciprocity relations actually are the same ones that you have in quantum mechanics, for a quantum mechanical beam going through some sort of potential in Schrodinger quantum mechanics. So we'll look fairly quickly at these reciprocity relations that are key to being able to talk mathematically in simple terms about mirrors and the light that goes through them and reflects off of them. We're going to need to develop some statistical concepts, and so I'll develop quickly the concept of the spectral density, which I used a little bit last term. and how it behaves when you filter a signal. When in each of these cavities basically filters the light and filters the noise, and you also do filtering and data analysis. And so the behaviors of spectral densities under filtering. And we're going to need to understand the uncertainty in photon arrival times. This delta n is square root of n gamma is the way I treated it here, associated with photon shot noise, the discreteness of photons, and we need to understand that in the language of spectral densities. And so in order to have the real tools to do quantitative instead of semi-quantitative analyses. So then there is an issue in general relativity of what is really going on in terms of the interaction of the gravitational wave with this instrument in general relativity. I just talked about arms increasing and decreasing in length. But this gravity wave detector is sitting here in the laboratory on Earth. It's not in a local Lorentz frame at all. And the only way we have of analyzing things at the present time is in local Lorentz frames. So we need to understand how we treat this honestly in general relativity when we're in an accelerated reference frame here on the surface of the Earth, refusing to fall freely, refusing to be in a local Lorentz frame. So that's the issue of the proper reference frame of an observer. And then I'm going to introduce in statistical physics the fluctuation dissipation theorem, which is going to be an important underlying tool for understanding noise. And we will see a sophisticated version of the fluctuation dissipation theorem, which is what we really need for LIGO, as well as the elementary version that you find in textbooks. So that's the fundamental physics I would like to get through in the next hour and a half tomorrow and half an hour today. If there's a little bit hanging over, then I may take it away from Alan Weinstein's lecture on Monday. But I want him to have most of the lecture to give a first overview of all the issues that you confront in a real interferometer. Okay, so that's where I'm planning to go. Any questions? Okay. So we can actually do all this physics fairly quickly. It's not really all that complicated. So let me begin with the issue of the general relativistic foundation. The issue of a proper reference frame. Well, the issue of the reference frame to be used, that is the coordinates, for a general relativistic analysis of the interaction of the gravitational wave. Last term, when we talked about the physics of gravitational waves, the polarization states, the motions of test masses in response to gravitational waves, we had two ways of doing this. We had a local Lorentz frame, and so the observer in a local Lorentz frame, you had to be freely falling. In the local Lorentz frame, you'll recall the space-time metric is the flat space metric plus a piece that is of order the Riemann tensor associated with the gravitational waves times the spatial distance away from the chosen origin of coordinates. And that's what the metric looked like. It was flat up to things that were second order in distance away from the origin. In terms of magnitudes, the Riemann tensor is the gravitational wave field with two time derivatives on it. And so this term here is h. X is the size of the interferometer. In a local Lorentz frame, I would generally, it would be my practice, to work in the local Lorentz frame of the beam splitter if the interferometer were out in space and falling freely. Then the x that I'm concerned about is spatial distance away from the origin, and I've got to have a frame that covers the entire interferometer, so it's got to go out a distance L along this arm and a distance L along that arm. These are small distances compared to 4 kilometers. And so this spatial distance x squared is an L squared. And h with 2 time derivatives on it is a 2 pi over the wavelength of the light if I set the speed of light to unity. Okay. So in this formula I'm setting the speed of light to unity. I need that squared, and then I need an L squared. And so that, let me rewrite this, is 2 pi L over lambda E squared times h. Let me remind you that in a local Lorentz frame, what happens is that the tidal forces associated with the Riemann tensor, so it's the forces actually associated with looking quantitatively at this term in the metric and seeing what are the forces, the connection coefficient forces that this produces. Those tidal forces move the test masses back and forth. This metric in the local Lorentz frame is as close to being Minkowski as is at all possible. And so if we think about things in terms of a local Lorentz frame, this is the closest we can come to thinking in a non-relativistic language. Space-time is very nearly flat. Tidal forces are like gravitational forces that push things back and forth. And we can ask ourselves in the local Lorentz frame, what does the interaction of the gravitational waves with the light do? Well, it modifies Maxwell's equations by a fractional amount that is of order this term here. By a fractional amount that is of order the deviation from the flat metric. And so, in a local Lorentz frame, the masses move by the usual delta L, which is 1/2 HL. Light is influenced by, say, things like a fractional change in the wavelength of the light that is of order this perturbation of the metric. So it's of order 2 pi L over lambda E squared times h. So long as 2 pi L over lambda E is small, then the light is not significantly influenced by the gravity waves, and we can think in a local Lorentz frame in a fully a non-relativistic manner. All we need to do is consider the fact that the gravity waves push the mirrors back and forth, and we can ignore the influence of the gravity waves on the light. So let's look for LIGO. What is the magnitude of this term? Well, for LIGO, that's 2 pi times 4 kilometers divided by just a second. What am I doing here? This is 2 pi over the gravity wave wavelength. Okay, and subscript E is the electromagnetic wavelength. There's a slight difference. The gravity wave wavelength is 3,000 kilometers, and the light is a micron. Okay. So this is 2 pi times 4 kilometers over 3,000 kilometers squared. Pi is equal to 3, and 2 times 4 is 10. So I have 10 divided by 1,000. I have 10 to the minus 2 squared. That's 10 to the minus 4. So the influence of the gravitational wave on the light is at a level of 10 to the minus 4 times h. Whereas the influence of the gravitational wave on the test masses is of order h. And so we can ignore the influence of the gravitational waves on the light when we discuss things in the local Lorentz frame.
How do we get to 10 to the minus 4 is small enough?
Well, it's going to make, well, let me put it this way. Suppose we're trying to measure a waveform. And we want, with what accuracy can we hope to measure a waveform? Well, you look at the signal-to-noise ratio estimates that we did last term, and we expect to get signal and noise. Let me start. We talk about signal and noise ratios that we can expect to have. The signal and noise ratios we can expect to have in terms of amplitude are up to maybe 100 in LIGO, up to maybe 10,000 in LISA. For LIGO, up to maybe 100. And so with LIGO, it's unlikely that these corrections are, at least in the era of LIGO 2, going to be detectable, just based on the signal and noise argument. One might want to go in and look very carefully to see for sure, but that's what you would expect. I've never gone in very carefully to see for sure. At MIT, they work in TT gauge. At Caltech, we work in local Lorentz frames. And so you can go compare the MIT predictions with the Caltech predictions. With the level of accuracy, we do the calculations, they agree. But well, let me go to TT gauge then and contrast what happens in the local Lorentz frame with TT gauge. You notice I'm still freely falling, and in TT gauge, I'm still freely falling. In this case, G alpha beta is equal to eta alpha beta plus H alpha beta transverse traceless, which is of order H. And in TT gauge, you may recall you proved on an exercise that the masses don't move. They are unaffected by the gravitational waves. You plunk them down in the coordinate system before the waves arrive. The waves go by and they remain at fixed coordinate location in TT gauge. However, the light is influenced in terms of coordinate quantities, things you would do in your computations, by, again, fractional amounts that are of order the deviation of the metric from the flat metric, so of order H. So light is influenced by amounts of order H. And so in TT gauge, it's the light that is influenced. In the local Lorentz frame, it's the test masses that are influenced. Now, when we go to LISA, we will work in a domain where L can be greater than or of order lambda. And so for LISA, we cannot use a local Lorentz frame analysis at all. But TT gauge works. There's nothing that inhibits the size of the detector in TT gauge. And so we will use TT gauge when discussing LISA. But for LIGO, there's a tremendous advantage to be doing everything without having to think about general relativity. The only thing general relativity does is moves the test masses, and that's all. And so that's why I prefer to work in a local Lorentz frame. Except I can't work in a local Lorentz frame because we don't fall freely in the LIGO laboratory. And so we have to deal with the fact that we don't fall freely in the LIGO laboratory. So I'm going to simply tell you that then you can simply transform to a reference frame which is accelerated upward with one Earth gravity relative to a freely falling observer. And that gets us into the laboratory frame. And so you just take a local Lorentz frame and then perform a transformation to a frame from local Lorentz frame to a frame that is accelerated upward with one Earth gravity, and you have the LIGO laboratory. And that is what is called the proper reference frame. Of the say the proper reference frame of the beam splitter. If I put the origin of my coordinates at the beam splitter, as I like to do. And I will just tell you what the metric then looks like. The metric then acquires a form ds squared is equal to minus 1 plus 2gz, where z is the upward direction, times dt squared, and everything else is unchanged. So plus 1 plus, say for plus polarization, 1 plus h plus of t minus z dx squared plus 1 minus h plus of t minus z dy squared plus dz squared. G is the acceleration of gravity, so it's the amount by which I must accelerate upward to prevent myself from falling freely. So in fact, it is rather simple to do that transformation of coordinates to a upward accelerating reference frame from the original coordinate system, and to see that this is the form of the metric. And then it's fairly simple calculations to verify that this G, this term in the metric, when you compute connection coefficients to get the equations of motion of test bodies, this gives rise to the downward gravitational force. It also gives rise to the gravitational redshift of light, and all the things that are familiar to you about ordinary gravity. Yeah.
Here you're assuming that the wave is coming in.
Here I'm assuming the wave is coming down from above. If it's and so in general it won't come down from above. And so let it still come from the z direction, which is off in some direction like that. And if I do that, then what I want to do is turn this into 1 minus 2 g as a vector dot x. G as a vector is down here. So if the z direction was up, this thing will have a sign flip because g is pointing down, and I have my previous formula back. And so this is really the way I should do it. If I have a wave, so if the direction from which the waves are coming is the z direction, or they're propagating in the z direction, and I just orient my coordinates in that manner, then for the plus polarization, the metric takes this form. The key thing is that in general relativity, the only thing that happens that is any different from what we ever did first term is throwing on a term that looks like basically a gravitational redshift term. G dot x is really just minus the gravitational potential, since g is the gradient of the gravitational potential aside from some sign. So this is 1 plus twice the gravitational potential times dt squared. This is not to be confused with, let me call that kind of phi, not to be confused with a phase shift. So you just throw on 1 plus twice the gravitational potential, Newtonian gravitational potential associated with that gravitational acceleration, that's all. When you work through the details of what this means in general relativity language, it means that just as in the local Lorentz frame, you can think about everything in a non-relativistic manner. All the gravity waves do is push the test masses back and forth. Similarly, in the proper reference frame of the beam splitter, you can think about everything in a non-relativistic manner. All this does is produces Newtonian gravity in the laboratory. And the gravity waves just push the test masses back and forth. And that's the whole story. Any questions? I'll give you a little reading on this for those who want to look at it in more detail. Let me turn to Gaussian beams then as my second piece of underlying physics. In my discussion of an elementary interferometer, I had laser beams that had to go out, go through mirrors, go through a beam splitter, go down 4 kilometers and come back. And if we're going to really understand interferometers, we need to understand the nature of those beams. And the kind of beam that we want to have is a beam that has 2 properties. First, we want to be able to keep it small. We don't want it to spread out all over the place because we want to keep our mirrors small. So the transverse size should be small. Now, transverse sizes will change over distance because of diffraction effects. If you have a very narrow beam, diffraction effects will cause it to broaden as it travels. And so we want to, and the amount of broadening that you have is constrained by the uncertainty principle. So if we have a beam at this location that has some cross-sectional size, let's call it delta x in the x direction, or delta y in the y direction. Then the uncertainty principle says that the photons in the beam have some uncertainty in the y component of their momentum that is greater than or equal to h bar over 2 times the transverse size. It's this uncertainty in the y component of the momentum, which says that some of the photons may have that momentum, but others have this momentum or this momentum. It's that uncertainty, that spread of momentum, that causes the beam to spread as it propagates. And but we don't want it to spread any more than it has to. And so we want a beam then, which has the property that you have an equality here and not a greater than or equal to sign. You want the minimum amount of spreading so you can keep your mirrors as small as possible. And a Gaussian beam has that property. So that's one great property of a Gaussian beam. It has the minimum amount of spreading that you could have. It has another very nice property. These are the properties. One, minimal spreading due to the uncertainty principle. The second property it has is that the phase fronts are spherical. They're pieces of spheres. So that as a beam goes along, and with initial size like that, and spreads, the surfaces of constant phase are pieces of spheres. So this is constant phase. It's a piece of a sphere. That means if you want to reflect the beam back on itself, all you need is a mirror that is spherical and has the same radius of curvature. So if you put a mirror right there, so that the surface of constant phase hits the mirror, this beam will just reflect back on itself and go right back down. And you will maintain then a Gaussian profile because it's just repeating back on itself. But the easiest kinds of mirrors to make are mirrors that have spherical surfaces. They're the easiest kinds to grind and to make as a practical matter, yeah.
So will it get narrow again?
So it'll get narrow again, yeah. Okay. And so, for example, in one of these arm cavities, the natural way to run things is in a way where the beam is narrowest at the center of the cavity, 2 kilometers down, and it's broadest here. So it has a profile that looks like that. So that is, it's big here, small there, but because of diffraction effects, it has to spread some. And the mirror just reflects it back down. It goes back and forth as an eigenfunction inside a cavity. So the fact that the surfaces of constant phase are spheres means you can build cavities with mirrors that are segments of spheres, and you can have eigenmodes of that cavity where the light just goes back and forth, folding on itself, maintaining a Gaussian profile in the transverse direction, and always having spherically shaped phase fronts. So those are the two properties, I think, that really make Gaussian beams the beams of choice, and why those are the kinds of beams that people use.
Could you say one thing about what it is about a Gaussian beam that's Gaussian?
Okay, so that's what I'm going to do now. So this was the key properties: minimal spreading and spherical phase fronts. Or the phase fronts are segments of spheres. Okay, so let me talk about the mathematical description of a Gaussian beam, and this is where you'll see what is meant by Gaussian. Now we're dealing with electromagnetic waves, and so the key physical quantities are the electric field and the magnetic field. Let's suppose the wave propagates in the z direction. We know these waves are transverse, and so you can have a wave that is linearly polarized in the x direction, in which case you're interested in Ex, which is some function basically of t minus z if it were a plane wave. Or it might be the y polarization, Ey would be some function of t minus z if it were a plane wave. This fact that you actually have two polarizations you can work with is used to great efficacy in interferometers in order to manipulate the light in ways that Weinstein will talk about on Monday and that will be discussed in later lectures. But for the purpose of discussing idealized interferometers, we just can get by quite happily with one polarization. And so I'll pick a polarization, say the X polarization, for example. And for simplicity, let me just call this psi, which would be a function of t minus z. So that's the field variable. It would be Ex or Ey. It could be Bx or By, whatever you wish. We know that Maxwell's equations say that the Cartesian components of the electric field satisfy the wave equation. So box psi, that is minus dt squared, plus the Laplacian squared of psi is equal to 0. So we're just dealing with solutions of the wave equation, but we want solutions that are not plane wave solutions like this, but solutions that have this property of having small sizes, minimal spreading, and spherical phase fronts in order to really be able to do things technologically that, with high precision. That's the kind of tool we want. And so I'm just going to tell you what this solution is. This is a solution of the Maxwell equations, of the wave equation. And it has the form let me first draw a picture of the profile of this beam. It looks something like that. There is some waist location where it has its minimal size, and it's going to spread going to the right and spread going to the left. As, for example, in the cavity that I sketched over there. Let me call z equals 0 this plane where it has its minimum size. Then psi at z equals 0 has a very simple form. It is just equal to e to the minus pi omega squared over sigma naught squared, where pi omega, I think I may have used it before, it's just an astrophysicist's version of x squared plus y squared. Pi omega is an omega with a pi grafted onto it. Okay. It's we think it's due to Chandrasekhar, who has a very powerful personality, and he left the imprint of pi omega on the astrophysics community. Okay. So it's the cylindrical radial coordinate. And this is a Gaussian. It's just it has the square of the transverse distance going away from the central axis. Pi omega is measured then like that. Okay. So that's what it looks like at the central plane. Then, as it goes out, its size is going to spread. Notice that sigma naught, then, is the radius at which psi, which is, say, an appropriate component of the electric field, dies by 1 over e as you go away from the center. So it's a beam spot size in that sense. Sigma naught divided by square root of 2 is the radius at which the light power, or flux, the energy flux, dies. Since the energy flux goes as a square of psi, it dies out faster. The square will die out faster than the field itself. Dies by 1 over e. Okay. So that's the meaning of this spot size, sigma naught. I guess many people call this W naught, and some people call that W naught, and some people call this W naught. Okay, so I don't know that there's a uniform, well, there is not a uniform, in the community I deal with, there's not a uniform agreement on what you should do. Now the spreading can be described by the transverse distribution down here a distance z. It has changed. It has changed so that the size of the spot, a distance z away from the waist, this is called the waist. The size of the spot at a distance z down from the waist is the original size times 1 plus z squared over z0 squared, or z0 squared then obviously is the characteristic length to the 1/2. the characteristic distance you have to travel. It's the distance you have to travel in order to increase the spot size by the square root of 2. Let's notice then that this is approximately sigma 0 at z less than z naught. And it's approximately sigma 0 over z0 times z at z greater than z naught. So it's sort of flat till you reach z naught, then it starts spreading out linearly with a spreading angle beta that is sigma naught over z naught. So the light just comes along pretty flat, then it starts to spread, and it has asymptotically a spreading angle beta. Now this spreading angle beta is well known to astronomers who deal with diffractive optics or others. The spreading angle beta works out to be the wavelength of the light over pi times sigma naught. That is, aside from a factor of phi, it's the ratio of the light wavelength, 10 to the minus 4 centimeters, to the size of the beam spot. So if you have a great big spot down here, you wind up spreading very slowly, a tiny beta. If you have a tiny spot down here, you spread real fast out there. And it's this same diffraction optics that governs diffraction-limited telescopes, the angular resolution of diffraction-limited telescopes. Okay. So if we then put in some numbers, so you can then just feed back and see what z naught is. Z naught then, knowing this standard relation for the spreading angle when you get out into the far region, then z naught is pi sigma naught squared over the wavelength of the light. Okay. So it's interesting to see what kinds of spot sizes we need for LIGO. For LIGO, we would like to have as small a size as possible on these mirrors, so the mirrors don't have to be too terribly big transversely. If we choose a waist size that is too small, then the spreading will be very strong and we'll have a great big size out at the end mirror. If we choose a waist size that's too big, you won't have much spreading, but you'll still have a big waist size out here, or a big beam spot size. So there's an optimal choice for the size of for the beam spot size of the waist in order to get the minimum possible beam spot size on the mirrors. So for the minimum spot size on mirrors, this is an exercise you can go through just with the math that I've got there. The minimum spot size on the mirrors works out to be sigma min, corresponds to an optimization where you have spread only by a factor of square root of 2 from the center. But I haven't yet told you how I should choose sigma naught. It shouldn't be too small and it shouldn't be too big. And that choice for sigma naught gives sigma min square root of the arm length of our cavity, lambda e, divided by pi. And if I put in 4 kilometers for the arm length, 1 micron for lambda e, this works out to be about 3.7 centimeters. So that sigma min divided by the square root of 2 then is about 2.6 centimeters. And so because of diffraction effects and our choice of a 4 kilometer arm length and a wavelength for light of 1 micron, we wind up with spot sizes on the end mirrors such that the 1 over e point in power has to be at least 2.6 centimeters, or in amplitude 3.7 centimeters. So the beam spot sizes are sort of like that on the end mirrors because of diffraction effects. And they're square root of 2 smaller on, in terms of amplitude, or in terms of the 1 over e point in amplitude. You can run your interferometer differently. You could choose the waist to be at one end, and you just spread out from there, but then you will definitely have a beam spot on the other end that is bigger than this size. So there are various reasons for wanting to run one kind of configuration or another, but the smallest you can get your spots, and if you make them equal so as to get the smallest possible spots on both mirrors, that's the size that you come to. Finally, the radii of curvature, the phase fronts, can be shown to be, and this will be in the exercises, z plus pi sigma naught squared over lambda e quantity squared 1 over z. This is a radius that is infinite when z is 0, and infinite when z is infinity, which just says that you go from a flat beam to something that begins to be curved as it's spreading out. Maximum curvature is reached at about the point where it has spread by a factor of square root of 2, and then it flattens again as you get out very far away. And the maximum curvature, so the minimum radius of curvature is here, and that minimum radius of curvature, I forget precisely, but it's of order 1/2 this distance, or it's of order this distance, minimum radius of curvature, which you can get from the formulas. Yeah. Okay, I'll continue this underlying physics on Wednesday. Thank you.